All right, well, we're back, and I figure I'll split this into two sections so that, in the case that it's like, hey, I don't want to sit in for the schools one, then you don't have to. So let's talk about, I'm going to talk about big O notation and benchmarking and things like that. These are just things that are good to know. And when you guys are ready, you can go ahead and, sleep the screens. So I figured I'll spend this first half talking about big O and benchmarking and code, things like that. And then afterwards, we can do schools, and you can choose whether or not you want to pay attention to that one. So real quick, if you are wondering who the TA is for the day, like each individual day we have, invites. Like if you don't have access to this calendar, let me know, because to this particular calendar. So all the TAs for each individual day will be listed underneath there. Unless they say otherwise inside of Echo Platoon. Generally, these people are, not generally, all of these people are working professionals. So if you need any help during the day, make sure you're just asking me and Mike and not bothering them at work. And then if you need any help after hours, there will be TAs for that particular day, except for Friday and Sunday. And then you can feel free to bother them on their day or specifically or their evening, but like the evening that they're supposed to be there. But outside of their hours, they're under no obligation to answer your questions. So just be aware of that. I also got a message from Leanna a little bit earlier that actually when she was interviewing at a position, they actually had whiteboarding, and it was Fibonacci. So I didn't know that. But that's actually pretty interesting that they actually do have that. So for a junior role, they will be asking you stuff like that. And for a junior role, they're also going to be asking you a lot about big O notation, which we'll cover right now. So big O and benchmarking is basically understanding how performant, how well does your algorithm run. And you will hear this quite often. And honestly, they're going to basically say, all these companies are going to say, like, what's the big O notation of this? What is the big O notation of XYZ? How do I get a better big O notation? It's basically, how can I get my algorithm to run faster and more efficiently? The amount of times you're actually going to do this in real life is close to zero. I was talking to a person named Bill Schofield, who works for Pivotal Labs, and he used to work for like a large gaming company. He wouldn't tell me which one, but he used to work for a large gaming company. And they had to write entire worlds into existence. I don't know. I don't understand how games are actually written. It's like they write entire worlds into existence. There's like laws of gravity that they write into there. There's like maps that they create, and like it's so responsive and so fast. Like he says you have to worry about the frames per second. Like, so if anything is wrong, like any algorithm is incorrect, your game is going to lag and it's going to slow down. So they're always worried about efficiency because they have to get everything's just so fast and so responsive, especially with modern day games. But even he said, like, the number of times I've had to like refactor my code because of big O notation being like a really big issue is very, very small. Like a lot of people try to like prematurely optimize their code to be like the fastest possible, when in reality it's never going to be read by that many people. But with that, like, you're still going to need to know big O because it's going to be an interview question, even though you might not ever use it in real life. So benchmarking is the act of timing your code. So I have a few things with benchmark here. I'm going to copy and paste it just to show you in just a bit. And basically what benchmarking does is it times your code. How long does it take something to execute? So we're basically looking, is your code slow? If it's slow, how can we improve the speed? Right now, your code is only impacting a handful of people, maybe you, your pair. If you were ever to use this in real life, maybe 5 or 10 people. But once you get into the thousands of users, and especially if your code relies on other code to run, which relies on other code to run, you have to make sure that your code is fast. So how does this apply to you? We want to write algorithms and code that's as fast as possible, code that uses as little memory as possible. And if you have a lot of bad code that executes slowly, your site's going to be slow. I think what they said was people have an average of like a 1 second patience level when it comes to a website. And you might say, like, that's ridiculous. Louis C.K. has this one thing. He's like, people are getting really angry when their website doesn't load very fast. He's like, we're shooting signals into space, and it's coming back down onto our phone. And people are complaining about 1 or 2 second like delays, but it's true. Like if you've ever been on a site that doesn't load just like that in a matter of milliseconds, oh, maybe they're down. I'll try again later. Or this website sucks. I say that all the time if it doesn't load within a second or two. So you have roughly 1 to 2 seconds to like load all of your code as quickly as possible. Otherwise your users may go away from your site. This is different for government things where it's like, please do not close your browser. It may take 3 minutes to do this. Like don't hit back or anything like that. Like certain things you can't get around. Like if you pay your taxes online, like if you pay Cook County tax, you have to just wait for like 2 minutes for them to go through the whole thing. But that's not the norm. So let's take a look at this code that we have here. I'm just gonna grab all of it. Grab this over here. Let's read through this code together. All right, so inside of Ruby, just like there's a CSV library that's built in, there's something called a benchmark library. A benchmark library is basically this giant B benchmark. It basically allows you to benchmark how fast your code is. Now I have 2 things. One of them just says print high, and then it just puts out high, and then the other one says repeat a certain number of times you provided a number, and then it'll say that number of times due puts high. And what I'm going to do is I'm going to just benchmark it 20 times, meaning I'm going to run through both of these blocks of code 20 times, take the average of it, and see how fast my code is. The first one, there's something called BM, which is benchmark, and there's a report. It'll generate a report out for you. These are 2 things that you can use to see how fast your code actually runs. Print high like takes X amount of time to run. Method 2, which is repeat times, I will just do repeat times. It takes this much time to do. So if all goes well, I expect this thing right here to be 50 times as long as this one, because this one is I'm just doing things 1 time. This one I'm doing it 50 times. Let's see what we've got. Ruby benchmark.rb. So it runs twice, and what we get is print high shows up 1 time, and it takes a total of 0.00030 seconds. This is how long it takes this particular bit of code to run. If we jump down to the bottom, it takes 0.00456. So you can kind of see like this very, very small difference between the 2. But one does take, it looks like, what is that, 50 times? More than 50 times? I don't know. 15 times longer than the other one to run. So you can kind of see when I run, it's kind of like no duh. Like if I run something 1 time versus running something 50 times, the 50 times thing takes a little bit longer. But this is a little bit of an example about how to use the benchmark library. So let's go back over here real quick. Center view. So when we talk about, so basically, if you take a look at these 2 resources, it's in your curriculum for today. This is basically, this shows you like just how fast different types of sorts take to run. So I'm going to speed this up a little bit just so you can kind of see, but I don't know if people can see this. There's 9 different types of sorts. So when you call like dot sort on your arrays and stuff like that, one of these 9 is powering them. There's different ones called selection sort, shell sort, insertion sort, merge sort, quick sort, heap sort, bubble sort, comb sort, cocktail sort. Like there's all these different types of ways that you can sort algorithms. So I'm going to play this real quick just so you have an idea of the code that you write really does make a difference. If I'm hopefully like when I want to sort something, I want to choose the most efficient algorithm. So turn up the music a little bit. Let's speed this up. Oh, it's too fast now. Wait, no, go back. So you can kind of see like the visualization here is essentially like you can kind of see quick sort, comb sort, bubble sort, cocktail sort. They're already finished, right? So if you were to write really inefficient code, something that took this quick sort probably less than a second to do, your selection sort is still running. And this cocktail sort may just take till the end of time, right? So you want to write code that's as efficient as possible. Is this still going? Okay, now it's done. So it looks like bubble sort is the least impressive one. If you take a look at other ones, you can kind of see there's other data visualizations. And you can watch this at your leisure if you're like super into like how fast your code runs or anything like that. But the general idea is certain things that you write are going to be faster than others. And the way that we measure that is something called big O notation. And big O notation, you can think of it as how complex your function is, which is the O portion, compared to the input size. So that's a really scientific example. It's the O is how complex is it going to be based on your index size, your input size. How long does it take to run? How complex is your code? So this is I found this great thing courtesy of Starhorn. Basically says there are many different types of big O notation, but these are the most popular ones. So if you do O to the 1, the speed doesn't depend on the size of the data set. So if I give you an array of 5 numbers or 5,000 numbers, an O of 1 would just be like take the first thing. It doesn't matter how big your input is at all. It's just like if I say give me the first thing, you can give me $1 million. It's kind of like what's a good example? If your first thing to do, if you were to receive money and every single time you receive money, you go out and you buy a double cheeseburger from McDonald's and it costs $1. This is a bad example. Does that make sense? O of 1, basically, no matter what size of input I give you, it's always going to be the same. If I give you an array of 1 thing or 50 million things, I tell you to give me the first thing, it's always going to take the same amount of time no matter what. O log of n, which basically means 10 times the data. Like, so I give you data and I give you 10 times the data. It only takes 2 times the amount of time to run through everything. O of n is basically a linear graph. Basically, if I give you 10 things, it will take you 10 times as long to run. If I give you 1 thing, it'll take you 1 second. If I give you 10 things, it'll take you 10 seconds to run. That's O of n. O n log of n means that 10 times the amount of data that I give you, if I give you 1 thing and I give you 100 things, it'll take you 20 times the amount of stuff to go through. O n squared is 10 times the data, takes 100 more times. And then O to n basically means that you wrote bad code. Let's take a look at some examples. So O of 1 is constant time, meaning that the amount of time it takes to run your code is going to be constant no matter what. Again, this is like if I give you an array of 1 number or 10 numbers and I tell you to return me the first thing, it doesn't matter how large your array is because all you're doing is giving you the first thing. So this is one called like, if this is an example that I came up with, like is the first element red? And I give you an array. The first thing is the first thing equal to red? If it is, return true, otherwise return false. So I can give you an array of 0 things, 1 thing, 50 million things. It doesn't matter how big your input is because all you're checking is that first one. A real life example is there was a small town in Africa, and this has been published in like the Wall Street Journal and stuff like that. There was a small town in Africa that was complaining about just how slow their internet speeds were. And they were like, it's so slow that we're actually going to have a pigeon race against our internet speed. So what they did was they started uploading let's say like a 50 megabyte document. So they started uploading it via the internet. At the same time, they loaded it onto a USB drive, stuck it onto like one of those carrier pigeons and sent the carrier pigeons to a town 50 miles away, which is where they were also downloading the stuff, where they would be downloading the same material. Can you guess which one got there first? Pigeon got there first. Otherwise, it wouldn't be a story in the newspaper. But that's kind of like, they were complaining, my internet's so slow, I can have a carrier pigeon carry over the information faster than that. But it's not actually a really accurate representation of how things work because the internet speed if I'm uploading something that's 50 megabits or 500 megabits or 500 gigabytes or something like that, it's going to obviously alter the time. The carrier pigeon has a USB thumb drive. You can put as much stuff as that on that thumb drive, and it won't impact how heavy that thumb drive is because it's a fixed weight for that carrier pigeon. It doesn't matter if you put one thing on there or 500 gigabytes of stuff. It's not going to change the weight of your USB thumb drive. So when you think of O of n or O of 1, it basically O of 1. Sorry, so O of 1. Think of the carrier pigeon and the internet speeds. It doesn't matter. The second one is linear time, O of n. It's going to grow linearly based on what you pass in. So you can kind of think of this as a graph that's scoping straight up, a straight linear graph. Hopefully this is what your investments look like. It's just straight up going like this. It's basically based on what you pass in, it's going to take that amount of time to run. So it's kind of like, if I give you an array, it's basically says like, if I give you an array of numbers and I give you a value, if it was like an array of 1, 2, 3, 4, 5, and you're looking for the number 5, I'm going to iterate through each individual one and return true if I actually hit the value. Now, if I do it 5 times, it's going to be a certain amount of time that it takes your code to run. If I give you 1,500 numbers inside this array and you're looking for some number, it's going to grow linearly based on the fact that I'm looking through more stuff. Your real life example here is more money, more problems. Like the more money you have, the more things you have to worry about, right? If you are a millionaire and you drive around a really nice car, you have to carry more insurance. You have to carry liability insurance so that someone, if they sue you, and then you have to worry about, am I going to meet a gold digger man or woman? It doesn't matter, right? There are probably more things you have to worry about when you have more money, more problems, linear time, O of n. And then O n squared is the other one that you need. This whole chart, there's a whole bunch of them here. The big ones are O of 1, O of n, and O of n squared. O of 1 is 100% constant. O of n, it means I'm just growing linearly. And O n squared means it's quadratic time. Based on the input that I give you, the amount of time it takes you to run will double every single time. So if you take a look at the code underneath, if I have an array of 4 items, it's going to return the code 16 times because I'm iterating through the code. I have one loop and then a loop within a loop. So loops within loops are generally speaking very, very bad. If you see your code having loops within loops, or if your boss sees it, they're probably going to let you know, hey, this is not the best thing that you can do with your code right now. Because it's going to grow. If I give you an array of 4 things, this is going to go through 16 times. If I give you an array of 10 things, it's going to take 100 times the amount of time that it would usually take. Obviously, if you have an algorithm that's less complex, it's going to help with your runtime and how fast your website loads. So again, this is a very short lecture, so we can get to schools. But the key takeaway. Let me finish this key takeaway, and then I'll get to questions. The key takeaways: if you search through a hash, it's faster than arrays because hashes don't have indexes. So that's one thing to keep in touch. Avoid nested loops, which is a loop within a loop, because it's going to take, O n squared the amount of time. And if you have code that has really bad big O complexity, like it's O n squared or O like 2n or something like that, you generally want to avoid that as possible and refactor. Aaron, you had a question?
No, I was just wondering if you could have a copy of this, of some of the breakdowns of notation.
It's actually in your curriculum. Any other questions on big O notation?
Why are hashes faster? Because they don't have indexes.
So it's kind of like if you had to keep track of the name and location of every single item, it takes a longer time than just being like, what's the name of all the stuff? All right. So
okay, so you're not thinking about 2 things. You're just like looking for the key and then you grab the value.
Exactly, yeah. Okay. So arrays, you have to worry about the index. Like it's going to be a fixed index every single time. You have to keep track of that. That requires some computational power. If you're just saying like, I have a whole bunch of key value pairs together, it's just kind of like, it's like if you had a list of all the people who got married today in Chicago, and you had a list of like 1 through 100, and you're looking for the spouse of of George or something like that, and you have to go through each person and find George, and then you have to find the spouse. Versus if you had just like an unordered collection, but just a bunch of like key value pairs of like, here's partner 1 and partner 2. All I have to say is like, who's the spouse for George? I find George, like George shows up right away, and then I grab the spouse for George.
And then what about nested if else?
If else does not matter.
Okay.
So basically what you're saying is that the computer will actually point to a key value directly rather than iterate through all of the keys.
Correct. Yeah. Hashes are faster for searching than arrays. They both serve their different. They both serve different purposes. Let's jump over to. With that, let me pause recording here and then start a new one so we can break up the recordings more easily.